Welcome to this video on deriving the Euler Lagrange equation. The Euler Lagrange equation is a fundamental result in the calculus of variations and forms the basis of Lagrangian mechanics. Let's start by understanding what this equation is and why it's important. In physics, we often want to understand how a system evolves from one state to another. Imagine a particle that starts at position A and ends at position B. There are many possible paths it could take between these points. The principle of least action tells us that the particle will follow the path that minimizes a quantity called the action. This principle forms the basis of Lagrangian mechanics and leads us to the Euler Lagrange equation. Let's define some terms. First, the Lagrangian L is the difference between the kinetic energy T and the potential energy V of a system. So we have L equals T minus V. The action, S, is the integral of the Lagrangian over time, from an initial time t sub 1 to a final time t sub 2. We can write this as S equals the integral from t sub 1 to t sub 2 of L of q dot t dt. Here, q represents the generalized coordinates of the system, q dot represents the time derivative of q, or the generalized velocities, and t is time. Now, let's formally state the principle of least action. The principle states that the actual path taken by a system between two fixed states is the one for which the action S is stationary, which typically means minimized. To find this path, we need to use the calculus of variations. We consider a small variation in the path q of t to q of t plus epsilon times eta of t, where eta of t is any function that vanishes at the endpoints, and epsilon is a small parameter. For the action to be stationary, its variation must vanish for all possible eta of t. This leads us to the Euler Lagrange equation. Now, let's derive the Euler Lagrange equation step by step. Step 1. We compute the variation of the action. When we vary the path, the action becomes the integral from t sub 1 to t sub 2 of the Lagrangian evaluated at the varied path q plus epsilon eta and its derivative, expanding to first order in epsilon. The variation of the action delta S equals the integral from t sub 1 to t sub 2 of the partial derivative of L with respect to q times eta, plus the partial derivative of L with respect to q dot times eta dot all dt. Step 2. We need to perform integration by parts on the second term to get rid of eta dot. The second term in our integral involves eta dot, which is the derivative of eta. We want to rewrite this in terms of eta itself using integration by parts. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. In our case, u is the partial derivative of L with respect to q dot, and dv is eta dot dt. So, the result is the partial derivative of L with respect to q dot times eta, evaluated at the boundary points, minus the integral of the time derivative of the partial derivative of L with respect to q dot times eta dt. Since eta vanishes at the endpoints t sub 1 and t sub 2, the boundary term is 0. Step 3. Now we combine the terms to get the complete variation of the action, substituting our result from integration by parts back into the original expression for delta S. We get that delta S equals the integral from t sub 1 to t sub 2 of the partial derivative of L with respect to q minus the time derivative of the partial derivative of L with respect to q dot, all times eta dt. For the action to be stationary, this variation must be 0 for all possible functions eta of t. The only way this integral can be 0 for all possible eta is if the integrand itself is 0. This gives us the Euler Lagrange equation. And there we have it. We've derived the Euler Lagrange equation. The Euler Lagrange equation states that the time derivative of the partial derivative of L with respect to q dot minus the partial derivative of L with respect to q equals 0. We can also write this as the time derivative of the partial derivative of L with respect to q dot equals the partial derivative of L with respect to q. This equation gives us the equations of motion for a system described by the Lagrangian L. It's a powerful tool that allows us to derive the laws of motion directly from energy considerations, without having to worry about forces explicitly. Let's look at a simple example to understand how to apply the Euler Lagrange equation. Consider a free particle moving in one dimension. The Lagrangian is just the kinetic energy, since there's no potential energy. So L equals 1/2 mv squared, or 1/2 mx dot squared. To apply the Euler Lagrange equation, we first compute the partial derivative of L with respect to x dot. This gives us mx dot. Then we compute the time derivative of this, which is mx double dot. Next, we compute the partial derivative of L with respect to x, which is 0, since L doesn't depend explicitly on x. Plugging these into the Euler Lagrange equation, we get mx double dot equals 0, which means x double dot equals 0. This is Newton's first law of motion. A free particle moves with constant velocity. To summarize, we've derived the Euler Lagrange equation from the principle of least action. The principle states that a system evolves along the path that minimizes the action. Mathematically, this leads to the Euler Lagrange equation. The time derivative of the partial derivative of L with respect to q dot minus the partial derivative of L with respect to q equals 0. This equation is incredibly powerful and has applications throughout physics. In classical mechanics, it gives us the equations of motion. In field theory, it gives us field equations like Maxwell's equations. In quantum mechanics, it leads to Feynman's path integral formulation. The beauty of the Euler Lagrange equation is that it provides a unified approach to physics, focusing on energy principles rather than forces, and works in any coordinate system. Thank you for watching.